As of lately, it seems that everybody is trying to tell you when and how the world will end. Some scenarios are far more familiar and likely than others. Those that are widely discussed in the media range from infectious diseases to nuclear war, all the way to collisions with massive asteroids. While they are all vastly different from one another, they all share one thing in common. They are all able to effectively end the human species once and for all. But all of these scenarios fall short when compared to one thing: black holes. We're all familiar with them, but what exactly is a black hole? Black holes are regions of space where the gravity is so high that the fabric of space and time has curved back on itself, taking the exit doors with it. But what does that even mean? And why are black holes black? Well, any large object, such as a black hole, star, or planet, has a certain escape velocity that is needed to escape the pull of gravity on that object. For example, Earth's escape velocity is about 11 kilometers per second. Move that fast, and you can escape Earth's pull and fly off to the edge of the universe. But chances are you'll probably be pulled in by something's gravity eventually, but that's not the point. The stronger the gravity an object has, the higher the escape velocity is. Now, black holes have some of the highest gravitational pulls in the entire universe. In fact, black holes are theorized to have singularities where gravity pulls you with infinite force, but we'll get to that later. Let's say somehow we made a black hole with the same exact mass of Earth, about 6 times 10 to the 24 kilograms. Alright, this looks good. Except this isn't to scale. It would look something more like this. In order to turn Earth into a black hole, you'd have to crush it down to about the width of your pinky finger, about 9 millimeters. So these two massive objects have the same exact mass, except one is the size of your finger and the other is the size of a planet. So how does this happen? When black holes are created, they are typically formed by the death of massive stars, those with about 20 to 30 times the mass of our Sun. While living, stars undergo nuclear fusion in their cores, fusing together lighter elements such as hydrogen and helium. This fusion of elements creates energy and pressure that pushes out away from the Sun, while gravity keeps the star held together. But as time goes on over billions of years, stars begin to run out of these lighter elements and move on to heavier ones. They begin to fuse together denser elements such as carbon and oxygen all the way up to silicon and iron. Except here lies the problem. Iron can't fuse with anything. There isn't any more energy being produced, so the power of the star's gravity takes over, collapsing the star under its own weight until it explodes in what we call a supernova. The outer parts of the star fly hundreds of thousands of miles into space, while the core continues to collapse under its own weight and becomes densely compressed. Remember how Earth has an escape velocity of about 11 kilometers per second? Well, if after all that, the core of what was the star is still massive enough, about 2.5 times the mass of our Sun, and dense enough, the escape velocity of the core becomes much greater than the speed of light, over 300,000 kilometers per second. This forms what we know as a black hole. An area of space is created where nothing, not even the fastest thing in the universe, light, can escape. But let's have some fun with it and dive into one. Imagine, just for a moment, that you are aboard a spaceship, but not any normal spaceship, one that can defy physics. One that can accelerate you to any extremely high velocity, even higher than the speed of light. This is completely impossible, but it's okay. Because you know your spaceship can reach any speed imaginable, you have no fear of black holes and decide to fall into one in the quest of science. You choose the supermassive black hole at the center of the Milky Way galaxy, Sagittarius A's star. This behemoth of a black hole is over 88 million kilometers wide, nearly 100 times as wide as our own Sun. A black hole of this size will give you enough time to observe it as you fall into it. At first, things might actually be peaceful, and here's why. Because of the black hole's size, at this point, the gravity isn't exactly going to be painful for you, but it will have a noticeable effect on the light coming from behind you. As you fall towards the black hole, you notice some unusual things. First, the stars behind you as you fall into the black hole begin to grow much brighter. The light from those stars is being pulled so strongly by the black hole's gravity that they begin to blue shift. As you fall further and further towards the event horizon, that is the point where our universe and the inside of the black hole meet, it begins to take up more and more of your field of view. It's almost as if the entire sky in front of you is filled with darkness. As you're about to cross the event horizon, you see the rest of the observable universe condense into one single, minuscule point directly behind you. If you were able to zoom in with your telescope onto this point, you would see the light from all the stars and the galaxies in the universe. But you would also see a very dim red glow. You remember this? This is the Cosmic Microwave Background, or CMB. It's essentially a map of the electromagnetic radiation left over from the Big Bang, the very instant that the universe came into being. The dim red glow you will see is actually this radiation being boosted into the visible spectrum. And then, finally, it goes dark. You have crossed the event horizon, and it's only darkness from here on out. You realize that it's time to get to work before you get ripped apart by the black hole's gravity. So you begin to observe, except you don't see anything. There is no light. The view out of your cockpit window is completely and literally black. There is nothing to see. There's nothing to observe. You began this journey to dive deeper than any human could into a black hole to discover what truly lies there. But there is nothing. You know the singularity of the black hole lies ahead, where our physics and mathematics fail, and you came to figure out why. But you can't. The answers are right in front of you, but you have no way of observing it. Your journey has come to an end, and it's time to leave this black hellhole. You attempt to turn your spaceship around and thrust away from the black hole at speeds not even light can match. But there's a problem. Your spaceship's instruments that are designed to detect the flow of gravity so you can orient yourself aren't exactly working the way you expected them to. They're supposed to be pointing you in the direction of the singularity, allowing you to turn directly around and escape. Except they're indicating that the singularity lies all around you. In every direction imaginable, gravity seems to increase. Up, down, left, right. 360 degrees of nothing but stronger and stronger gravity. The point that you are currently at is the weakest that gravity will be for your future self. Every direction points further and further towards the singularity and your inevitable death. Clearly there's a problem with your instruments. This can't be true, can it? Except it is. It is true. Once you cross the event horizon of a black hole, there is no leaving. The three-dimensional coordinate system that we use in our universe doesn't work. Time does not flow similar to the way we experience it here in the normal universe. Time flows downwards, towards the singularity. The curvature of space-time inside the event horizon. Every direction that is theoretically away from the singularity would ultimately carry you backwards in time, into the past. This is the true definition of an event horizon. Once crossed, there are zero. Literally 0 points where there are trajectories that face away from the black hole. There are only trajectories that pull you in deeper and deeper. The singularity is all around you, and it is getting closer.